طيب بسم الله الرحمن الرحيم. Last time we talked about the multimedia delivery schemes, and we talked about dynamic and static channels, and we talked about the difficulties of guaranteeing quality of service for dynamic channels, and we also talked about packet switched and circuit switched networks. And we said that for circuit switched networks, when we set up virtual circuits, the advantage of this is that we can provide some guarantees on quality of service. And then we started talking about the most common matrix that we use to measure quality of service. And these are not new matrix. So we know some of them. So we talked about bandwidth, and we said that bandwidth is the capacity, it measures the theoretical capacity of any channel, whether this channel is a wired or wireless or anything. Okay, so this is the theoretical capacity of the channel. At runtime, you may not get this capacity at full, and that's why you may end up with some variations especially in wireless. You end up with some variations in the throughput that you get, and that's why we have the concept of dynamic channels. We started talking about packet loss, and we said that packet loss has some reasons and some sources for error. One of them is the network congestion, and if we have any transmission error due to some interference, whether or on wired channel or wireless channel, so you have some interference, and that affects the signal that goes along the air or along the wire, and based on that, you may get some errors at the receiver side. And of course, if there is only one bit in error, we consider the whole packet has error, and we have to drop it. Okay. Another source of this packet loss, as we discussed last time, is the packet circulation. Okay, and that happens when the routers they have inconsistent information across the network. They did not reach to a stable state where all the information in all the routers are consistent across the entire network, in which case some routers may route the packets in a wrong way, and the packet may end up being circulated, and it never reaches the receiver. Okay, so today, inshallah, we're going to continue talking about the matrix that we can use to quantify quality of service. And the third one is the delay. Delay is a very critical component, and it's a very important component, of course, especially for multimedia applications. The end-to-end delay includes delay encounters by when we talk about the delay, we talk about the latency that one packet encounters along the way. Okay, why we stress on the concept of one packet here? Because this is the main difference between the delay and the jitter, which we will talk about in the next slide. So a delay measures the latency that one packet encounters when it goes from the very first stage when the packet gets generated. Who generates the packet in the first stage? The application, right? Until it reaches the application on the other side, right? So this whole end-to-end latency is what we call delay, and sometimes we call it packet delay because it's associated to one packet. This delay we can divide into 4 different delays. Okay, so the end-to-end delay. So we have when we talk about the layers, we have the application layer for the source. So this is the source, and we have the application layer all the way to the physical layer, and then we go to the destination, where we have again the application layer all the way to the physical layer. Okay, so the packet gets generated here. Okay, then it has to go all the way to the physical layer, and then it goes through the channel, And remember here, the channel is end-to-end. You may have some routers here, you may have some switches, something like that, right? And then it goes to the physical layer of the destination, and then it goes all the way up until it reaches to the application. Okay? So this whole path is divided into four different delays. Okay? So this delay is divided into 4 components. So the first one is the processing delay. The processing delay is the time that's taken for the packet to be processed in all layers until it reaches the physical layer. Okay? So any processing that happens along this way is what we call a processing delay at the source, because there is another processing delay at the destination. That's again the processing delay until it goes all the way to the application layer on the other side. So these are processing delays. Usually this processing delay is negligible. It's nothing compared to the network-based delays. Okay? So there is the transmission delay. By the transmission delay, we mean that the physical layer gets stream of bits, right? We know that the physical layer deals with bits, right? So it deals with the path along the way as one pipe. Okay, so in this pipe I can insert the packet in bits. So transmission delay talks about the time between the first instance of time when I put the first bit on the line until I finish sending the last bit on the line. This is what we call transmission delay. The transmission delay is calculated based on the bandwidth of the channel. Is based on the bandwidth of the channel. And usually the transmission delay, it gets calculated as the length of the packet that I'm trying to send over the bandwidth of the line. So this bandwidth is the capacity of the channel, and the length is the length in bits of the. So bandwidth is measured as what? Kilobits per second, right? So I can send this much kilobits per second. Okay? So how much time I need to send L bits is L over B. So this is the transmission delay. So the transmission delay is based on the bandwidth of the channel. Type. So this is the third component. The fourth component is what we call network transit delay. Actually, this delay on its own is divided into multiple parts. Okay, the network transit delay is divided into what we call propagation delay and router processing delay and queuing delay. So what happens is that the network transit delay is once the source finishes putting the last bit of this packet over the line, the transmission delay is done. And now the packet is on the network, is on the line of the network. Yeah, let's imagine that this is the beginning of the packet and this is the end of the packet, and now it's on the line. Okay? But as far as the source is concerned, the physical layer of the source has finished sending the packet over the line. Now the packet needs to find its way over this line to go to the destination. Well, before the packet reaches to the destination, it may actually go through 1 or 2 or 3 or 4 or maybe hundreds of network devices before it reaches the final destination, right? So these could be routers, could be switches, could be anything. And it can encounter wireless delay, wire delay, and so on. So the propagation delay is the time that the packet gets to propagate to reach to the first network device, to reach the physical layer of the first network device. Okay? So it's like at the end of the day, the packet gets transferred as signal. So we know that the packet is transferred over the line in a form of a signal, whether it's an optical signal or a electric signal in the case of wired, or electromagnetic, bravo, in the case of wireless. So these are the three forms that the packet eventually will be represented by over the line, whether it's a wired or wireless or fiber optics and so on. So the propagation delay is the delay that the signal takes to propagate from one location to another across a wired or wireless channel. Okay, type. There is the router processing delay if it reaches to a router. In that case, the router will have to perform routing, right? So routing requires that the router has to schedule it and will have to say, okay, so this is a multimedia application, so I should give it a priority. So this logic requires some certain amount of time, and this is what we call router processing delay. Okay. Once it processes the packet, it places the packet on a queue, and this queue is the queue that's connected to the output port, so that the packet can wait for its turn to go out from the router. It's like exactly when we go to a bank or when we are going into the immigration in the airport. So there is a guy in the front who says, okay, so you go to this queue, you go to this queue, right? So what this guy is doing is actually scheduling. He's scheduling all the packets that are coming to go in a specific output port. Okay? So he tells me, okay, you go into that queue, you go into that queue, and so on. Once I go to that queue, I have to wait for my turn, because there might be some people in front of me. So I have to wait until my turn comes, and then I get output from the airport or from the bank. Okay? So these are the different components of a delay that only one packet encounters to go from the application layer in the source to the application layer in the destination. Okay? So the question now is, which component is the largest component, or is the key component? That actually depends on some factors. It depends on heavily on the type of the transmission medium we're talking about. For example, if we're talking about satellite communication, okay, which is the largest, the propagation delay or the transmission delay? Propagation, by all means, of course. We're talking about satellite, come on. Satellite has to go all the way up and then all the way down. Though the propagation delay is the largest for sure. Okay? Versus if we're talking about wired, propagation delay is nothing. It's nothing. It's almost zero. It's negligible. Transmission delay is the key. It's the bottleneck. Okay? In all cases, in most of the cases actually, processing delay, whether at the source or at the destination, is almost nothing. So we almost never talk about processing delay as one of the key components in the packet delay. Almost never. We always talk about either the transmission delay or the network transit delay. And for network transit delay, it depends whether we're talking about one hop or whether we're talking about end-to-end. For end-to-end, definitely the queuing delay and the router processing delay becomes an issue, because we have to go across multiple routers and switches and stuff, and for each stage we have to go into a queue, and we have to get scheduled and then go to the output queue and so on. So this delay becomes significant. Any questions? Okay, so this is the total packet. So just to appreciate what is the difference between delay and jitter. Well, as we said, delay is the latency encountered by one single packet. Versus jitter, it talks about the inter-packet delay. the inter-packet delay. So I don't care about the absolute delay of one packet. I care about the difference here. The difference between these packets is what I care about. So it's not by one packet, and I care about this difference. So this difference is actually my jitter. And of course, usually the jitter is this difference, and then I get the average. Okay, so from the moment that I generate, so if I count or if I evaluate the time from packet 1 to go from the sender all the way until it reaches to the receiver, this is a packet delay, right? If I calculate the difference between the packet delay for packet 2 and the packet delay for packet 1, then what I'm actually calculating is jitter. So jitter is the delay variation. So for many of us, delay variation is kind of new. You probably didn't know about that before. I expect you to know very well packet delay. We discussed this many times. But delay variation, maybe not. Maybe most of you have not heard about this before. So why do we talk about it now? Well, it ends up that jitter and delay variation is key for multimedia applications. In some cases, even more important than the delay. Let's see why. So this example here illustrates the concept of the time when I first generate the packet. So imagine if this sender is a camera, okay, and this camera is generating raw video information. And this raw video information, it gets sent over the network. And as we all know, the typical types of networks, we cannot guarantee that each packet will encounter the same path, will go through the same path, which means that each packet may encounter different delay. So here, it shows you the effect of this phenomenon. So imagine if a sender generates packets like this with delay between these packets, which is almost constant. Okay? This delay between the packets is almost constant. This is at the sender. What happens at the receiver is that these packets may go through different paths, may encounter different delays, so they arrive in this situation. Why? Packet 1 has delayed a little bit, but packet 2 was really fast. So the packet delay between 1 and 2 becomes less than the source. Okay? But unfortunately, packet 3 have been delayed a lot after that. So it was unlucky that it went through a different path and it took a longer time. So the inter-packet delay between 2 and 3 was really long. Okay? But then 4 came after it with a pretty reasonable delay. So the question is now, what should the receiver does? Well, we're talking about multimedia application. So imagine that this is like a real-time video. So now the receiver has these 3 choices. Okay, so the receiver has 3 choices. Choice 1, the player, the player software at the receiver side is dumb. Is dumb, is stupid, sorry, is not thinking really efficiently. So what it does is that once the packet comes, it plays it. Okay? So this is option 1. Okay? So in option 1, as we can see, the distance between 1 and 2 is even less than the distance that they were generated. What does this sound when you hear or when you listen to a video like this? You see parts of the video are playing very, very fast, right? And then from 2 to 3 is very slow. So how do you think the quality will be? I did not lose anything in that case. Remember that. All the packets are there. I did not lose anything. So I should be good. But do you think this is good? From the quality point of view? So between packet 1 and packet 2, it's playing very fast. It's like you were watching a game, and then before you actually realize that there is a goal, the ball was inside the goal. So you did not really catch the moment. You didn't have enough time to catch the moment. This was very fast. But between here and here, you were waiting and waiting and waiting, and nothing's happened. So of course, this will be interpreted as very bad quality, although I did not lose anything. Right? So option 2 will say, no, I don't want this quality. So the player will say, let's take into consideration, now the player is a little bit smarter. The player will say, let's consider in the play time at the receiver, the time that this packet should really be played. بمعنى إن packet 2 arrived earlier than the time that it should be played. Right? Here, it arrived earlier. I will not play it at this moment in time. I will delay the play out of this packet to be played exactly in the time that it should be played in, which means that this distance is similar to this distance. Okay? Which will be reflected as, for you, as someone who is watching this, is that, okay, so I can cope with the speed of the play. So I can cope with the player. I could realize that, you know, the ball is moving and the ball is entering the goal and so on and so forth. So I can follow what's going on. But this player does not store anything, which means that it has one packet, whether to play it, or to play it now, or to delay it, or drop it. Okay? And now, after a specific amount of time, I should be expecting packet 3 to arrive. But packet 3, remember, was delayed. So, okay, so, alas, it missed the chance. I cannot play it. Okay? And then 4 arrives just on time. So I was able to play it. So do you think the quality here is better than here, or here is better? So A is better than B, or B is better than A? B is better. Especially if it's video.
Yeah,
if it's video,
something is missing. Yeah.
if it's something is missing, what will happen?
You can tolerate that.
You can tolerate that. Your eye will kind of tolerate this. Why? It's a scene, it's a big scene, but maybe part of the scene is missing somehow. Our brain can sort of process this and average out so that it can give you some comprehension about what's going on, even if it's missing. So video has high level of tolerance when it comes to, if this is audio, I would agree. Audio is very sensitive. Audio is very sensitive to packet loss. If you lose one packet, this means that there's like 2-3 seconds of audio you will not listen to. You will not be able to listen to. Why? Because audio is small. I can store 2 seconds of audio in one packet. So if one packet is lost, I lost significant amount of information of the audio. And in that case, your ear will realize this much faster. Okay? But generally speaking, at least I play the packets in the time that they should be played. So, well, maybe I can tolerate a little bit to some extent, and I can live with that. The optimal case is if I have what they call a de-jitter buffer. So this is called what? This is called de-jitter buffer. So this does the opposite of the delay variation. It tries to smooth out the effect of the delay variation between the packets. So what happens is this buffer will store maybe 10 packets or 50 packets. And then and only then it starts to play these packets. When it plays the packets, it plays it in the time that they should be played. Right? So if you try this, packet 1 will be played at the right time. Packet 2 will be played at the right time. Packet 3 will not be missing because I can always get it from the buffer. But the start of the play is delayed a little bit. And this typically what happens. when you download a YouTube video, you never watch it at the moment you press on play, right? You have to wait for, what is this time? This is called the de-jitter buffering. De-jitter buffering. So buffering, although it's a very simple technique, but it's the most effective technique to cancel the effect of jitter. Okay? This is the most powerful technique ever to cancel the effect of jitter. So for all multimedia applications, de-jitter buffering is one of the most powerful techniques. However, for streaming video, this is very effective. But as we will see in a minute, in some applications that require constant interaction, okay, the de-jitter buffer will be okay, but you will feel that there is some kind of delay, because what the de-jitter buffer does is that it delays the start of the play. Okay, it takes some time to store the packets into the buffer, and then after some time it starts to play. But once it starts to play, it relies on the fact that whenever I want to play a packet, I will find it in the buffer. Okay, so it tries to smooth out the effect of the jitter. But I have to pay a cost. What is the cost? Is that I have to delay the start of playing these packets for a few seconds.
It stores all the packets and the...
Not all. You have to wait for 2-3 seconds at the beginning, and this heavily depends on on your connection. It heavily depends on your connection and on the packet delay, or the average packet delay. If the average packet delay is long, the de-jitter buffer technique will have to wait longer time to store enough packets in this buffer, so that when it decides to start to play, there is a very high chance that packet N, when I need it, I will find it in this buffer. If this buffering is done optimistically or over-optimistically, what will happen is that I will store 3 packets and then I will start to play. What will happen? Maybe packet number 10, when I look for it in the buffer, I will not find it. Because I was over-optimistic at the beginning. So that's why I'm saying there is a technique behind it. It's not, so I don't store all the packets, no. I'm not supposed to, otherwise it's not real time. Okay, so de-jitter buffering, really, it does not eliminate completely the effect of jitter, but it does like magic in many cases to loosen out the effect of jitter for multimedia applications.
So the digital buffer is something implemented in the network or in the receiver?
No, in the receiver, not in the player. It's the application layer. It's not in the network. The network has queuing in the router and everything. There is queuing, right? But this is from the network point of view. This is an application layer thing. It's not, and that's why there are some players that are almost dumb, and any effect from the network, you would feel it right away in the player. And some players are very efficient, because this buffer, the buffer size and the amount of time you store these packets, these two parameters have to be calculated really carefully. They depend heavily on the packet delays and on the speed of the network and many things. From this, you can say, okay, I need this amount of buffer and I need to store this number of packets in the buffer before I start playing. Because I can be over pessimistic and say, I will have to store the entire video, right? But come on, this will be very bad quality. I mean, for the user, I'm not gonna wait forever for these packets to be stored in the buffer, and also, I don't have this enough buffer to store all the packets, right? So the length of the buffer and the time of collecting these packets in the buffer have to be calculated really carefully. Okay. But we know that this buffering is very essential. Any questions?
Mm-hmm.
that it buffers at the beginning and then it starts playing whatever it buffered, and then is it possible that while playing it buffers the rest, what the video is playing?
While you are playing, it happens, and it happens to many of us, right?
But sometimes
While you are playing, you see like some pauses. What happened is, well, there could be a chance that I'm trying to play a packet and I go to the buffer and the buffer is empty. I don't see the packet in the buffer. In that case, I don't have a choice. I have to wait. As a player, I have to wait. What else can I do? I'm supposed to play a packet right now, but I don't have it in the buffer, so I'll not play it. And what happens is that the player, the time that this packet should be played in is stored in the packet. Usually, طبعا this depends on the format of the video or the audio, but typically in many formats, the relative time actually, is stored in the packet. So when I receive the packet, I will know when to play it.
this happens that it stops, but my question is, while playing, can it buffers?
Yes, of course. Yes, of course. This is the whole idea. While the player is playing something, it's also storing. And that's why all the players are multi-threaded.
Okay, so
You know the concept of multi-threading. So there is one thread that's playing the packets, and there is another thread that stores all the incoming packets into the buffer.
okay.
So a thread will go to the buffer, it finds the packet, it reads the time, so it knows that I have to play it now. So I go and play it. While I'm playing it, the other thread is storing other packets into the buffer.
So the reason of it stopping while buffering in the middle might be the connection, right?
Connection, yes, of course. Of course. Of course. While the player is playing something, it goes into the buffer, it finds nothing, which means that the network is very congested and I was not able to receive the other packets on time. So in that case, I will give the user pause and nothing is played. So what else can I do? So that's why the jitter is a very important phenomenon in multimedia applications. And as I said, the de-jitter buffer and the parameters associated to it, how much time should I buffer and everything, depends heavily on the type of application. So we will talk about the requirements of the multimedia application by which I need to be either very conservative in buffering many packets, or I have to take some risk and buffer fewer packets so that I don't have to wait forever to start playing. Because if I wait forever to start playing, I lose the quality, and then also the user perception will be very low. Imagine if I'm talking over the phone. So this is a very interactive application. So the person is trying to say something, and I'm supposed to hear back some replies. But there is always a delay, and this happens if you listen to Al Jazeera or something, and always the reporters, if they are very far away, and there is that big effect of jitter, you feel like they are not following on each other. It becomes really hard, right? So nothing is lost. The communication happens, but it's just that there is very long delays, and if the application requires interactivity, it becomes really hard to follow. Like you see someone is talking in the middle of the other guy is talking and stuff, it starts to get a little bit corrupted. So this that's why jitter is very important for multimedia applications. Type. So in order to understand this a little bit more, we will divide our applications into constant bitrate applications and variable bitrate applications. By constant bitrate applications, we mean that these are the applications that generate packets homogeneously or with a fixed bitrate, which means that the rate that is coming out of the source is constant. Looks like this. The rate that is coming out of the application is constant. What is an example of constant bitrate applications? For example, if we're talking about uncompressed audio or video, because if you compress the video, it's variable in nature. It's variable bitrate. But uncompressed audio, imagine like uncompressed audio is typically like this. Our audio is like It's like a signal like this, and what happens is that our signal will be converted into samples. So it's based on the sampling rate. So each sample is represented using bits and stuff. So sampling, if I take the samples and deal with them without any compression technique after this is called the uncompressed audio, right? Like only I'm dealing with samples. So I get the sample the audio, send it over the network. So this is constant bit rate because all these samples will be represented using bits, and the bits will be sent homogeneously. So for every sample, because inter-sample time is fixed, right? So we know from the sampling theory that these samples, they get generated every fixed amount of time. Okay? So the samples, I send them over the network, so this is fixed or constant bit rate. Okay? If we convert the audio into MP3 or something, that's different. Okay? So an example of audio which generates constant bit rate is uncompressed audio. Uncompressed video is the same thing. Again, we deal with pixels. Right? And pixels, they get converted into colors, and colors, they get converted into bits, and the bits will get transferred. So no compression here. Okay? In that case, it's fixed bitrate or constant bitrate. Okay? So these are applications that generate constant bitrate. So in that case, so for constant bitrate, the user satisfaction will be what? The user satisfaction will be like a step function like this. Why? If I give this application, if the network gives this application a rate less than the rate that it uses to generate the packets, the user will not see anything. Okay? I'm expecting like fixed samples with fixed rate, and I'm not getting this. So if I'm not getting this, my user satisfaction will be very low. Until I reach to until the network gives this application the rate that it requires. In which case the user satisfaction will jump high, and will it stay like this? Why? Because it's fixed, right? In variable bitrate, we talk about examples of this are most of the multimedia applications are variable bitrate, right? So because most of the except if we talk about even telephony, they use some kind of compression. So any type of compression relies on the fact that the video applications, there is a small difference between one frame and the other, right? So they send the first frame and then they send the differences. So the differences will be small. So that typically, if we use any compression technique, the video rate will be like this, and it will go up, be like this. So it's variable bit rate, right? So all the compressed audio, video, and so on, they use a variable bit rate. Inherently, they use variable bit rate. So in that case, there is a minimum bandwidth before which I did not give to that application the minimum amount of bandwidth that it requires in order to get anything moving. Because it's variable, so you have maximum rate and minimum rate. Before this minimum rate, the user satisfaction will be very low, almost nothing. Okay? If I give a little bit above the minimum bit rate, like this one, so I give a rate which is like here. So if I give, again, so عشان بس في ناس مش متخيلة قوي. So imagine if I have a video with bit rate like this. Okay? So if the network gives a bit rate here, this bit rate is below the minimum bit rate, which is this one, right? So in that case, it's like I give you a pipe and you cannot send anything into it. So the user satisfaction will be almost zero, right? And then after the minimum bit rate, if I give you a rate which is like this much. So at least you can send this much you can send, okay? So the user satisfaction will start to increase gradually. If I give you a bit rate here, it will be almost maximum. If I give you a bit rate here, خلاص, you will not increase because you have reached, you can send all the maximum bit rate instantaneously, so you will not get more satisfied. After this point, you will not get more satisfied, right? So for constant bit rate, we get this step function. Before the rate we're expecting, nothing happens. And after this rate, we have fixed satisfaction. For variable bit rate, it varies a little bit. Okay? So typically, as I said, multimedia encoders, so once we put some encoders, whether this is video encoding, audio encoding, and so on, we typically get variable rate channel or variable bit rate. Okay? So if we have variable rate channel, we may be able to get constant quality. Why? Of course, this is a very simplified assumption. This relies on the fact that the network is extremely small, which does not exist. The network is extremely smart, that when the video needs more rate, I will give it more rate. When the video needs less rate, I will give it less rate. So it's like this variable rate channel, which is the dynamic channel we talked about, from the network point of view, gives the network resources based on this rate, exactly. So it sort of follows the variable bit rate that the source generates. Channel video generates inherently variable bit rate, right? So if the network gives exactly this rate, the user will see constant quality. The user will see constant and high quality, right? Because he will see all the video content and everything is seen with the maximum resolution possible. Okay? This is the ideal case, which almost never happens. Almost never happens. Okay? The suboptimal case or the non-ideal case is when the rate of the channel is fixed. In that case, you have variable quality. Why? Because I give you a rate which could be like here. So in that case, anything below this, you will see it with the best quality, right? Anything above this rate, well, it depends. If you have good de-jitter buffer and if you can delay and buffer some packets and stuff, you may get by and introduce some delay. But definitely, it will affect the quality a little bit. So when you have ideal variable channel that gives exactly the source what it needs, then you get constant quality. But this almost never happens. So this is a more typical scenario. This is a more typical scenario. And that's why I'm not sure if you have noticed, in some cases when you watch YouTube, you see the video, sometimes it's blurry a little bit. And then after some time you see everything is, right? What happens is that in video there is the concept of I frame and B frame and P frames and stuff. So if you get the I frame, you get the best quality. You get the best quality. If you get B or P frames, you get blurry. You get quality, but it's not good. So when you start listening, you may get B and P frames in the beginning until you start receiving I frames. Once you start receiving I frames, you see the quality has improved drastically. And then from then on, the quality has stayed the same almost. Okay? So this is based on the fact that your channel your channel provides in a way some constant bitrate. But the video inherently is variable bitrate. So you see variable part. That's typically what happens. Okay? طيب, we'll stop here.